This video is for example ramp problems. Part 1 is the front of the paper that we probably already did in class, and then part 2 is the back of the paper that you should be viewing for homework. Okay, we're going to do some example problems for an object sitting on an inclined plane or a ramp. So as usual, the weight of the object is always down. When we say down, we mean toward the center of the earth. Sometimes I don't even draw the object. I'll draw it now. So since my motion, the motion of the object, it's not straight up or straight down, and it's not straight left and straight right. If this box is going to move, it's either going to move up or down the ramp. So because the motion is not up, down, left, or right, it's more convenient to impose a tilted coordinate system with one axis parallel to the plane and the other perpendicular to the plane. But now when I go to write my equation, if I have a net force, I want it to be here. This weight, that's not going to be on the axis. And I know that's what's going to pull it down, part of the weight, a component of the weight. So I break this into components, just like I did when we first learned about vectors before we did projectiles. So I'm making a good box. You want to focus in on that and make sure you're truly making a rectangle. Right angles, parallel sides, yep, that's a rectangle. And remember, the whole point of the rectangle is to show you how long to draw your components. So I'm breaking my weight into components. So instead of that one black vector, I have these two pink vectors. And I'll name them. Instead of naming them X and Y like I did before, now I'm going to name them weight perpendicular, and that's weight perpendicular to the plane. So this is weight parallel. Weight parallel to the ramp. So now remember, that black one is not here anymore. I don't have the resultant anymore. I've replaced it with these two components instead, because these two components are equal to that one resultant. And then you can tell if the block pushes on the ramp pushes on the block. That's the normal force. But the ramp's not pushing straight up, it's pushing this way. That's what normal means, perpendicular. It's supporting it perpendicular to the surface. So normal force is this way. So normal force is not equal to the length of weight. Normal force is equal to the length of weight perpendicular. The perpendicular component of weight. And then there might be more forces to add to that. There could be friction, somebody could be pushing on it, there could be a string tied to it. I mean, there's other kind of forces we could have, but that's kind of the basics. So down here, the normal force is always perpendicular to the plane. Let's try an example problem. So what is the acceleration of 75 Newton object down a frictionless 35-degree incline? So we're looking for acceleration. We know we need a net force. Well, weight is not on our axis. We'll start by breaking that into components. So 75 is the weight. I'm making sure I'm making a rectangle. So I've got weight parallel to the plane and weight perpendicular to the plane. So these two pink ones instead of the black one. I didn't even draw the box this time. I'm just drawing all the forces on the box. So I've got the supporting force of the ramp, which is the normal force. And it says it's frictionless. There is no friction. So that's it for forces. So in this problem, the normal force equals weight perpendicular. That's a new one. And weight parallel equals the net force. That's the force that doesn't cancel out. That would be the force that causes it to accelerate. You don't have to push on something for it to accelerate down the ramp. A component of its weight accelerates it down the ramp. So we have to start by breaking that weight into components. What I usually do on these is I make a little list. Whenever I have an angle and I'm going to be breaking things into components, I'm going to make my little list. I'm always going to put weight and mass on the list. And then I'm going to put on whatever it is that I'm breaking into components. In this case, it is weight that I'm breaking into components. So unless it's a tricky solve for M problem, I will always either know the mass or the weight. And if I know one, I can find the other one. You can tell in this problem I know weight. I know the weight is 75. So I'm looking at this triangle. Remember in class I showed how whatever this angle was, this angle was. And I know the hypotenuse here is the weight. So the hypotenuse is 75. So if I want to break into components, that's going to be sine and cosine, where this is the opposite side and this is the adjacent side, and the 75 is the hypotenuse. I know the weight is 75 already. So my opposite side is weight parallel. So sine is weight parallel over hypotenuse, and my hypotenuse is the weight, 75. And my adjacent side is weight perpendicular, and my hypotenuse is still the weight, 75. So I'm looking at that yellow triangle, not just memorizing. So now I grab the calculator and cross multiply. So sine of 35 times 75 equals 43.0 if I'm going to keep 3 sig figs. And cosine of 35 times 75 is 61.4. So I'm going to put them over here on my list. I usually don't even write all this stuff. You can go right to your calculator and do that. That's fine. But that's why it's nice to have this handy list. So if I know weight, I can get mass. I'm just taking 75 divided by 9.8. I'm using the equation F equals ma. So I divided both sides of the equation by 9.8. Okay, so I've got my list of stuff. I'm ready to solve. I'm looking for the acceleration of the object. So I'm going to pick my net force equation down here. I'm going to put in my little equation for Fnet. Fnet equals ma. I'm ready to fill numbers. I know weight parallel is 43. I already found that. I know mass is 7.65. I already found that. So now I'm just solving for A. Divide both sides of the equation by 7.65. And I get my acceleration is 5.62 meters per second squared. Let's try the next example. 50 Newton objects, so that's the weight of it. And start by breaking my weight into components. Drawing a good rectangle. I'm drawing my components the right length. So weight parallel to the incline, weight perpendicular to the incline. Okay, so this, I have acceleration again, so I know I need a net force. And this time I also have friction. So friction opposes the motion. Oh, remember if I know that angle, I know that angle. So I'm looking at this triangle when I go to break into components. The object pushes on the ramp pushes on the object, and that's this, the normal force. And this problem has a coefficient of friction, so I have a friction force. The object, if it's accelerating, nobody's pushing it. It doesn't say anything about anybody's pushing. So I know it's going to accelerate down the ramp. So if it's moving down the ramp, friction is going to be up the ramp. And I know it's smaller because I need a net force. So my equations from the diagram. The normal force equals the weight, perpendicular, and weight parallel minus the friction force is the net force. Common mistake here. People want to go start putting this W in an equation. Remember, this W is not here anymore. We replaced this one black one with these two pink ones. So we're only looking at the pink forces when we write our equation. Let's make our little chart. Always the mass and the weight, and then whatever I broke into components. And in this problem, it's the weight that I'm breaking into components. So I'm given the weight is 50. If I take the 50 divided by 9.8, I get that the mass is 5.10. I'll show the work up here this time. So I'm doing F equals ma, where F is the weight, 50, m is what I'm looking for, and A is 9.8, weight, 9.8. So I divided both sides by 9.8. That's how I got the 5.1. Now I'm looking at my yellow triangle to break into components. My opposite side is weight parallel. My hypotenuse is weight. And I know my weight's 50. So this is 50. I should have labeled it. And cosine is adjacent, which is this side of the triangle, over hypotenuse, which is still 50. And now I just do my cross multiplying. and I'll add those to my list. So sine 35 times 50 is 28.7. That's my weight parallel. And then cosine 35 times 50 is 41. That's my weight perpendicular. I'm bringing up my equation from the diagram. Weight parallel minus friction force equals the net force. I'm going to write a row and substitute in little equations. Friction force is move times the normal. Net force is ma, F equals ma. And now I'm going to add numbers. Weight parallel, that's up in my list. That's 28.7. Mu, the coefficient of friction is given in the problem, 0.24. Here's a common mistake. Normal force was almost always equal to weight. It's not. Normal force is equal to weight perpendicular. So make sure you're putting in normal force is 41, not 50, 41. Mass is in my list, 5.1. And this is the acceleration of the object, and that's what we're looking for. So now it's just a math problem. I'm going to multiply and I get 9.84. And subtract over here and I get 18.9 equals 5.1a. Just going to make myself a little room here. I'll divide both sides by 5.1 and my answer is 3.71 meters per second squared.